Okay, so last time we covered Rankine earth pressure theory. Today we're going to cover Coulomb theory. And then we're going to cover the log spiral method. We're not going to get too theoretical in the log spiral method, but I want to go over it briefly and show you when it's important. And then the last thing we'll do today is come back and do a quick review over some summary of Coulomb and Rankine, and I'll also go back to talk about how we solve earth pressure in layered soils, which we blew right through at the end of the lesson last time. I think we'll have time to do it again today. Okay, so Rankine is a different earth pressure theory than Coulomb. We use them both. So the main goal today is not only to understand Rankine earth pressure theory and where it comes, Coulomb earth pressure theory and where it comes from, but also how it differs from Rankine and when it's more appropriate to use that. So that's the main difference. And Coulomb has different characteristics that you'll see, and it should make sense where you want to use it and why you want to use it. So we're going to start with our same little model of our magic wall that was wished in place with a height h. And the easiest way to understand Coulomb theory, I think, is to think of it as a graphical analysis. So we're gonna do this as sort of a graphical analysis, and then we'll derive the equations and solve the analytical part. So we're going to assume that we have some failure wedge here and an angle theta from the horizontal. There's some total active earth pressure here acting. This is a wedge analysis, so we're going to have this wedge back here. The vertical force from the wedge there is the weight of the soil. And then on this failure surface, there's a normal force and there's a shear force. And we're going to use this axis system in an M. We're going to use both that and the XZ axis system, but we're going to start with that one initially. So we're going to start by doing a summation of forces, and we'll start in the n direction. So in the n direction, S has got to be equal to W sine phi. That's the proportion of the weight plus PA cosine. Sorry, that's theta. PA cosine theta. So we're working in this axis system right here. And in the m direction, summation of forces equal to 0 is going to give us n. The normal force is going to be W times cosine theta plus the active earth force, the total active earth force times sine theta. Now, if we have just a frictional soil, then the total shear force that I can have on that failure surface, realize this is a limit equilibrium analysis, so we're going to assume that there's a failure at the surface, because again, this is a limit. We're looking for the limit when the soil is just at failure, just like we were doing for Rankine. So in that case, S is going to be equal to N times the internal angle of friction. So we're just going to make this substitution in for S, and we're going to get S is equal to W cosine theta plus PA sine theta times tan phi, because this is my normal force, and there's tan phi, right? So I'm substituting this in for N. So then I set that equation equal to this equation on this side, and I have W sine theta minus PA cosine theta is equal to the quantity W cosine theta plus PA sine theta, all times tan phi prime. So somebody told me you guys have figured out how to download a program where you can undo the hiding that I do. Is that right? No? All right. So what are we looking for? We're looking for PA because we want to, be able to calculate PA. So we're just going to solve for PA. If I solve for PA, that'll be W times sine theta minus cosine theta tan phi over cosine theta plus sine theta tan phi. So that gives me PA. I can rearrange that factor out I can get rid of the cosines and sines and turn everything into tangents by doing a little geometry manipulation on this and end up that PA is equal to W times tan theta minus tan phi prime over 1 plus tan phi tan theta. Or that's just PA is equal to W times tan phi minus tan theta. And then I'm going to calculate that the weight, right? The weight of this W is going to be the weight of the triangle here. The weight of the triangle here is just 1/2 base times height. So that's 1/2 gamma h squared cosine theta. All right. So I'm going to put that all together. And that gives me the active earth pressure force is 1/2 gamma h squared cosine theta tangent of the quantity theta minus phi prime. And I'm just going to transpose that on the top of the next page in just a minute. So all I've done here is use summation of forces in the in the m and n direction equal to 0 and the weight of the soil. That's all I've done. Okay, so there's a same equation. So I want to find now when this is maximum, right? That's what we're trying to find. Because I can have different theta angles. You know, the failure surface could be here, could be here, could be here. And I want to find out when it's maximum. So what I'm going to do is I'm going to take the partial of the active earth pressure with respect to theta. And if I do that, that's this equation. And then I'm going to set that equal to 0, because where it's 0, that's a maximum or a minimum, right? So I'm going to set that partial equal to 0, and I'll find out that the critical angle, wow, that's a nice angle. It looks like a familiar one, right? The critical angle where I'm going to get a maximum PA is 45 plus phi over 2. Woo, that's nice. That's always reassuring when you do something the other completely different way and you get the right answer. So, and when I plug that back into the, I'm not going to go through all the math, but when I plug that back into my equation for the active earth pressure force, I'm going to find out the PA is 1/2 gamma h squared times 1 minus sine phi plus 1 sine phi, which should look familiar, right? So Ka is 1 minus sine phi over 1 plus sine phi, which is the same solution as Rankine. Isn't that nice? We're a half an hour into the class and 4 slides in, and we've just proven the same thing that we knew from last class. But this is the simplified version, because what do we do here? We assumed we have a horizontal ground surface, and we assumed that PA was horizontal too, right? Now, I don't have to have, I've made some assumptions here that I don't have to have. I assume the angle of PA, but I could assume another angle for PA. There's no reason that PA has to be horizontal. I could have put it at any other angle here, and I could have solved the equations just that if that's a fixed angle. I didn't need to make that assumption. So that's one of the flexibilities of Coulomb. We're going to do the same. We're going to do the same solution with this one with cohesion. And then we're going to make it more general by allowing changes in the slope angle and changes in the orientation of PA and also changes in the back slope of the wall. So if we have cohesion, I've got the same equations for the summation of forces here, but for the cohesive soil, the shear force is now equal N tan phi plus C times L, where L is the length of the surface here, right? That's the only thing that's changed, is my shear force now has both cohesion and frictional component, right? Everybody with me? Otherwise, it's the same. The weight of the wedge hasn't changed. L is going to be h over sine phi. If this is, sine theta. If this is theta, we know h. So the length L is going to be h over sine theta. So I'm going to plug that in here, and I'm going to get that PA is 1/2 h squared cosine theta tan of theta minus phi prime minus C times h divided by this whole mess. And if I, again, do the differentiation, I'm going to get the same critical angle because C is not a function of anything. That's just a constant, right? The C term is a constant. It's not a function of theta. So that's going to be a constant. And I'm going to get this equation for the active earth pressure, which should look familiar again. And guess what? That's exactly the same as Rankine, right? Where this is for Rankine for a horizontal ground surface, Ka is 1 minus sine phi over 1 plus sine phi. And so this is 1/2 gamma h squared Ka minus C times h times the square root of Ka, exactly the same as Rankine. So notice I'm coming to the same solution with a completely different assumption. I'm not assuming, in this one, what I'm doing is I'm assuming the directions of the reactive force and this planar surface, and then I'm just finding that surface on which the horizontal stress is maximum. But I'm coming to the same answer that we got in a Rankine theory. We were assuming that the soil behind here, all the soil behind here was in a state of failure and using more Coulomb failure envelopes. So a different approach. Okay, let's now, that's nice, but if all we're doing is getting the same answer as Rankine, it wouldn't be much use to us. So let's talk about how it's what makes it more useful. So if there's movement and the wall, if this is the active case, the wall is actually moving in this direction, right? Well, if the wall is actually going to move in that direction someplace, this wedge is actually going to move. This wedge is actually going to slide this direction, and it's going to actually slide down the wall. The wedge is actually going to move in that direction. Relative to the wall, the wedge is going to slide down the back of the wall, and it's going to slide on this failure surface. And if it is sliding on here, there's going to be some vertical component to the wall, and PA is not going to be horizontal. So there's, I just messed that up, so I'll erase this. So there's going to be some upward force. It's a downward force on the wall, or it's an upward force on the wedge as the wall moves. It's going to be some frictional force from the wall friction. And so the resultant is that PA is not going to be horizontal, but in the active case, it's going to be angled up. And we call that angle delta usually. It's called the wall friction angle, or sometimes just the wall angle. So Coulomb recognized this, and what he did was he solved this problem by assuming constant angles of delta. So you can just assume what delta is. What's the maximum delta could possibly be? Well, if for a cohesionless soil, the most it could be is phi, right? But it could. But if you're If you're building against smooth concrete or steel or something, it'd be less than phi, but the most it could be is phi. Right? If there's cohesion there, then there's an adhesion term that you've got to account for. And realize if we go back a slide here, let me go back to one more slide. When we derived our equations, if PA wasn't horizontal, we would just have another angle in here. If we have a delta in here, then when I sum forces in the m and n direction, I'm just going to have another term in here that's going to be related to delta. It's not going to change anything. I know delta. We're going to fix delta first. So we can solve the problem. It's just got another term in it. So that's what Coulomb did. So the big difference in Coulomb is that he assumes delta is constant. But the other thing that you can do with that is you can assume you don't have to assume that delta is constant. The back slope angle does not have to be horizontal, and the back of the wall doesn't have to be vertical either, because once you have to know what alpha are, you have to know alpha, you have to know beta, and you're going to have to know delta. I think that's the next one. Theta, where's my delta? You're going to have to know delta, but once you know those angles and they're fixed, they're not unknowns. And so you're going to go through the same derivation that we did before. It's going to be a little more complicated because you're going to have some other terms in it, but all those terms are going to be constants. They're just going to be transcendental functions of alpha, beta, and delta. And the reason Coulomb developed this theory was at the time that he was doing this in the 17th century, they were building big, massive gravity walls, and they looked like this. They had a back slope and a front slope onto them, and he realized that the soil was going to slide down the back slope, and so it made sense for him to look at this analysis. So the little short derivation we did, where we formulate, we use summation of forces x equal to 0, summation of forces y equal to 0, and then we find theta critical, and then go back and calculate the earth pressure. It's the same process, except now we've got these other three variables in the process. So when we do that, we get this really nice equation for the active earth pressure coefficient. And if we do the pass, and I've given you, I think I've posted a summary table. One of the things I'll do is check during break that I posted. I posted a nice summary table of all the equations for Rankine and Coulomb. So you don't have to write those down. So if it's a passive case, now the wall is moving this way. Well, now the wedge is going to actually be sliding up, and it's actually going to be moving up this direction. So the wall friction angle is going to be the friction angle, the direction of the wall friction is going to be the other direction, because now it's actually pushing down on, instead of pushing up, it's pushing down on the soil because the motion's in the other direction. And you get this number for the passive earth, this equation for the passive earth pressure. So it's got a lot of variables in it, but alpha, delta, and beta are all fixed by your geometry of the problem you're solving. So it's phi for that matter. So it's not that hard. It's just tedious. Okay, well, let's make sure we go through the assumptions here. So the first assumption is that the soil is isotropic and homogeneous. The failure surface, that back slope that goes back, is planar. The whole process was derived based on that. I'm sorry, the slopes, both the failure surface and the slope are planar. If you go back to here, the derivation for when I derived the function for w, I assumed that this was planar back here. So with this closed form solution, when we find phi critical, that assumption's in there. So both the slope angle and the failure surface are assumed to be linear for this. We just did this derivation for total stresses. But we can do it for effective stresses if the groundwater surface is horizontal. If there's flow, the derivation's not exactly correct. So when we derived this thing and we found an analytical solution, so we just derived it with sum of forces is equal to 0. We're not summing moments, we're just using two equations. We found an analytical an analytical situation solution for finding the critical failure surface theta. But we can do it graphically without that. If the assumptions for, in particular, if the back surface isn't planar, we can do a graphical solution. And I'll show you that. I'll show you it with it planar, and we'll show you it another way too. And so the way we do this is we know that the angle between the normal force and the friction force has to be at an angle of phi, or phi prime, right? And so we're going to resolve those into that direction. And we know the direction of the resultant here. So we know the direction of all three of these forces. So what we're going to do is we're going to take a trial wedge, such as this one. We're going to take this trial wedge. We're going to plot the weight. We're going to have to do this to scale, so there'll be so many pounds per inch or kilonewtons per centimeter. So this is the vector for the weight of the wedge. I'll just measure the area of that, multiply by gamma. I know the direction of PA, so this line is parallel to this line, and I know the direction of R, so that line's parallel to that line. So where those intersect, this triangle has to add up to 0. So when the way those add up, all I've got to do now is I take this. That value has to be equal to PA. This value is equal to R. I'm not really that interested in R, but this vector here is equal to R. And so if I'm concerned about, oops, I guess I wrote those in there. I don't know that that's the maximum, right? That's just one wedge that I did. So now I can change theta. I'll decrease theta. So when I change theta back, let me clean this slide up. Whoops. I'll move theta back. When I roll theta back in this direction, the weight's going to get bigger, so the weight will be here. The direction of PA is not changing. But the direction of R will be different now because the slope angle is different, right? So I'm going to do that, and each time I do that, I'll get a new point here that's the intersection, and I'm just looking for the maximum PA. So after I've done this a few times, I'll just draw a line. I'll just draw a curve there that connects all the values of P. So each one of these is PA for a different wedge. And all we have to do is figure out where PA is maximum, so it looks like that's the maximum PA, and that would be the active earth pressure. What's nice about this, you understand what we're doing here? It's just a graphical solution to those two equilibrium equations. Now what's nice about that is our analytical solution for phi critical, we had to assume the back surface was planar because we had that equation for the weight as the area of the triangle in it. But what's nice about this solution is if I have some non-planar back plane or surface like this that might be stepped and it's got roads and all kinds of stuff in it, I can use the graphical solution. I don't need to have an analytical form for the weight. I am going to have to measure the area. And I can even have a surface load on there. That's no problem. So all I'm going to do in this case, so here's a wedge. I've got this weight here. I have to resolve this surface weight into some W2, I should say. And this thing will actually have to have two vertical weights. So W2 would here, and this would be W. In other words, you have to add both these weights. But they're both vertical weights. I know the direction of them. I still know the direction of PA, and I know the direction of R, so I can calculate this. And I'll have to use this area to compute A. But if you're doing this on a CAD program, you can just ask it for what the area is. So it's a very convenient method for calculating active earth pressures for arbitrary backfills and arbitrary different loading conditions. So I'm just going to, again, I'll just keep changing theta, and the weight will keep getting bigger. And I keep, for every wedge, I find the locations where these intersect at these points. And again, I'll just draw, once I've clearly got a bunch of them, I'll draw a curve through them, and I'll come in here. And the maximum point may not be one that you computed at. It could be in between. In this case, it looks like pretty much like this is the maximum. So that's PA right there. Well, I guess in this case I decided that the maximum was a little lower than that. Whoops. And we'll talk about this later as a graphical way to calculate loads from induced stresses too. Now, we don't do graphical solutions too much anymore because they're time consuming compared to running some kind of a computer program to do this. But this is a really convenient method, and when you're doing this, sometimes some people call this a trial wedge method. What you're really doing is just a graphical solution to Coulomb's method. And all you're doing is summing forces in the x and y direction equal to 0, and you're doing that implicitly with your little triangle here. You're implicitly doing that. And then you have to do you're doing a graphical minimization or maximization problem here to define where the maximum is, and you're going to have to assume several of these. But it's not hard to do. And actually, it's not that time-consuming to do with a CAD program, because once you've got the thing set up, you just draw lines, ask it for areas, and you can do all the work that way. Someplace back in my files, I have homework problems from my earth retaining class in the 1970s. No, I guess it was 1980s, with all these things done with pencil and ruler and. So that's Coulomb's theory. Questions about Coulomb's theory? So what are the big differences in between Coulomb's theory and Rankine's theory? Wall friction. This is the big one. And then we have the advantage of, since it's a summation of forces one, we can do this graphical solution with it. But the big difference is wall friction. Other than that, the assumption is the same. The soils, we're still using more Coulomb failure criteria. We're still using we're still assuming that the failure surface is planar. By the way, you can do this when there's cohesion. When there's cohesion, let's see. Let me go back a little bit to there's just one of these, and erase the. Whoops. So if there's a cohesion term on here, the cohesive force is just going to be equal to C times L, where L is this length, right? Well, we're going to know L because it's a graphical. We're going to know L, and we're going to know the direction. So your triangle just has another term in it. You're going to be able to plot. This is going to be C times L. You're going to plot that there, right? It's not. I mean, your force summation. You're going to have C times L, and now you're going to know the angle of PA is not going to be different. So now this is PA. And actually, the better way to do it. Let me change that. The better way to do it is to. Let's see. I got to think about this now. No, I think you have to do it that way. I'm trying to think about this now. Yeah, because you've got to have all the known. Yeah, you're going to have to do it this way. You're going to have, see, it's going to be this way. This is going to be C times L. You know the direction of PA, and now this right here is PA. So you come to your next wedge. C times L is a little farther back. Now this is PA. Now the only trouble with this one is it's a little harder to figure out where the maximum PA is, because the PAs don't all start from the same place. But you can do the same thing. You can do cohesion on this without a problem. Okay, cool. Let's go ahead and take our break now, and then we'll cover log spirals and pass and compare the three methods afterwards.